Okay, so the recording is going, and it's a pleasure to welcome Anubhav Mukerjee from Georgia Tech, who will tell us about embedding 3 manifolds in symplectic 4 manifolds.
Okay, thank you very much for the invitation. And this is officially my first talk on my research. I have given a few other talks, but this is sort of the official first talk. Uh, and this is my first talk using slides. So if you feel that I'm going too fast, please stop me, and I'm happy to explain anything what you request me to. So today I'll discuss my recent work on embedding of 3 manifold in symplectic 4 manifold. So the basic conjecture which is proposed by John Etner, Hume Min, and myself was that every closed oriented smooth 3 manifold smoothly embedded in some symplectic 4 manifold. So the question is that why one should care about such a conjecture? So first of all, I will give some motivation. One is the classical motivation why this is interesting, and the other one is from the modern mathematical perspective, that why one should care about such a conjecture. So the classical perspective is following. Embedding of 3 manifolds in higher dimensional space has always been a fascinating problem. Witness embedding theorem says that every 3 manifold can be smoothly embedded in R6. Hertz improved this result by proving that every 3 manifold smoothly embedded in S5. And meanwhile, Licorice and Wallace proved that every 3 manifold smoothly embedded in some 4 manifold, in particular connected sum of S2 cross S2. Around 1980s, Friedman came up with his amazing result that which in terms proved that integer homology spheres topologically embedded in S4. After this, even shortly after this, Donaldson's diagonalization theorem and later by Rocklin invariant, it was shown that there exists integer homology sphere which cannot smoothly be embedded in S4. So this is sort of the first time when this smooth versus topological embedding arises. Um, so a natural question arises that, okay, fine, that we cannot embed in S4 for sure smoothly, but does there exist a compact 4 manifold in which all 3 manifold embeds? For example, if you think that 2 manifolds, that is surfaces, can be embedded in a fixed 3 manifold. Similarly, recently proven that all the 4 manifolds also can be embedded in a fixed 6 manifold, in particular CP3. So one can hope that maybe there exists some 4 manifold where all the 3 manifold can smoothly be embedded. Um, but Xiaomi gave the answer as a negative that there doesn't exist any such manifold, 4 manifold where all closed 3 manifold can be embedded. So because of that, one can think of such an embedding problem in a infinite.
Sorry, Anubhav, did you say that Xiaomi result is a recent result or
No. It's an
old?
old result.
Yeah.
It's around 90s.
Do you
Okay,
know
yeah.
anything about how you possibly prove such a thing?
It's sort of some kind of algebraic topological abstraction.
Okay, all right, that's
Yeah,
good.
so it's sort of very algebraically topological
Sure.
abstraction. So thus one can think of such embedding problem in a large class of 4 manifolds. And now we know for a fact that symplectic 4 manifolds form a very interesting class of 4 manifold. So this is sort of a classical reason why we care about this problem on the first place. Now here is the modern reason and the reason how we came up with this conjecture. Um, so in particular, for a closed 3 manifold, by fixing a spin C structure. So spin C structure, in a vague way, one can think of spin C structure as a non-vanishing vector field on the manifold, a choice of a non-vanishing vector field on the 3 manifold M. Since closed 3 manifold M has Euler characteristic 0, such an non-vanishing vector field always exists. So spin C structure exists in particular. So given a closed 3 manifold with a fixed spin C structure, Oswald and Szabo has defined one kind of particular kind of homology, which is known as Higard-Floor homology. In terms, this particular Higard-Floor homology turns out to be a very powerful three-manifold invariant. And it has these four flavors, that is hat, plus, minus, and infinity. Although in this talk, we'll not talk anything in details, but two things I want to mention. So roughly speaking, for a rational homology sphere, Y, with a particular spin-C structure S, HA plus, that is the plus version of the Higard floor. So H stand for Higard, F stand for floor. So HA plus with the plus version of Higard 4 is a F2U module. So where F2 is Z mod field of order 2, and U is sort of an element of order 2 in the multiplication element with degree 2. And HA plus Y is roughly speaking have this structure of T plus direct some mysterious element here. So let me say what is T plus. Oh, by the way, this mysterious element has all the utors, and that means all those elements. So there is a natural U accent on HF plus, and this mysterious object contains all those elements which sort of vanishes after some possibly finite times of U multiplication. Okay, so in other words, it looks like kind of this tower, which is T plus, and these branches, which are elements of this reduced object. And the U action is sort of sending each element up to degree 2. So you can think of this way, that the U action sort of preserve this tower, whereas after sufficiently many times the U action sort of vanishes this element to 0. Okay. Similarly, one can think of HF minus as this infinity tower in the negative direction with a few branches coming out. Okay, so this is sort of a very hand-wavy idea of what is HF plus and HF minus. And I'm not going into any details of the definitions. Now, the one good property is that there is a nice isomorphism between these plus reduced elements and the minus reduced element. And for that reason, we call this as HF rate.
Can you go back? So why I would think when you have torsion, like why is that, like why are you visualizing that as something that comes off of your red line?
Oh, I mean, yeah, so this is not particularly the correct picture, but yeah, I mean, it's not necessarily, it could be somewhere here also, like away from the branches as well. So it's not particularly the correct thing, but there is another way of thinking this, sort of like looking at the long exact sequence of HF infinity, HF minus, HF plus, HF infinity, and HF plus. And they are sort of, if you see those accents, they are, you can see that the kernel of the map from HF infinity to HF plus is sort of these elements. But did I sort of answer?
I guess I'm also just confused. Like if I take I'm guessing each of these dots represents one dimension, like some generator of homology. If I take U and I act on like a point where, like a trivalent point, where does it go?
Oh, yeah. So I feel that, yeah. So this is maybe not the correct way of describing. So yeah. So essentially, these red dots are going down by the degree 2 map, and yeah. So okay, I feel that, yeah, this is not the correct way of drawing. And here, if I take this element, that will come to here after the U action. Yeah. So
Okay.
yeah. So this will come to this. Yeah. Okay. Yeah. So yeah, this is a wrong way of drawing the picture, I feel. Yeah.
Great. Thank you.
Oh yeah, I guess like I can imagine there being a basis change where your arrow, like you had like two things and you act on U, when you act on U, they go to the same thing.
Yeah.
Because they differ by something that's in torsion. So you'd have like,
yeah.
I just thought like your graph should like.
Yeah, this is, I just wanted to say that there are some branches and there are this main tower. yeah, but this is a wrong interpretation what I draw here. And another interesting fact is that there is only this finitely many such branches other than this main tower. Okay, so these are the things what we need to know in order to understand rest of the stuffs. So the interesting part is that for the 3-sphere S3, there is no such branches. That is HF red part is 0. So the plus is just this tower, infinity tower going up, and the minus is this decreasing tower going down. Okay, so Osbach-Zabor defined a 4-manifold invariant using this, which is also called F-mix or mixing variant. So if I have a 4-manifold W with a boundary Y, I can kind of take a 4-ball out and think of this sort of as a cobordism from the top boundary S3 to boundary Y. And in particular, I can also assume a spin C structure on W such that that induce another spin C structure on the boundary Y. So in particular, this cobordism induce a map from the minus flavor of S3 to the plus flavor of YS. So I'm not going into the very details of this map, but under some certain condition, this is in fact a well-defined map. Oh, sorry. So in this particular map now, as we saw that HF minus is just an infinite tower. So we kind of take this generator, call it as theta minus, which is a unique generator in HF minus S3, and we can look at its image under this cobordism map. And we kind of track that element. So under some certain condition, this is actually a well-defined map, which is also invariant of this cobordism. And this extra condition, what we need is that this B2 plus of W strictly bigger than 1. So what is the meaning of B2 plus W? If you never saw this, so you think of that in W, there is sort of a embedded closed surface with self-intersection number positive. And there are at least 2 of those surfaces in W. So that kind of indicate what is the meaning of B2 plus W bigger than 1. So this is sort of giving you a invariant. But notice that the image, so in this case, we are looking at what is the image of theta minus under this map. So one obvious question one could ask is that if I fix an element in HF plus YS, does there exist a 4-manifold W such that eta is in the image of the mixed map? So this is also indicating how one can think of the Higard-Floor.
You haven't defined the mixed map. You've just defined a cobordism map. Is that what you mean?
Oh, so I'm saying that the image. So here mix means sorry. So F mix in this case is theta minus. So this is sort of yeah. So yeah. So this image is we call.
I see you. I see you just like the cobordism map is on HF minus, right?
Yeah. So
you see really it's a minus to plus thing that I've never understood.
So this is sort of the cobordism map going from the minus version to the plus version, and we kind of considering its image.
It's the cobordism map together with that connecting homomorphism from through the
so secretly, secretly I'm kind of not saying how this map is going, but here is the way this map one could think. So you kind of take an admissible cut, whatever that means. I'm not.
No, you don't have to define what an admissible cut is. Just
Yeah. So it's sort of kind of coming from HF minus S3 to HF minus Y, and that is actually factoring through that box, minus version of the box to the plus version of the box, and then it lands to HF plus of Y prime, and then from here it is going to HF plus of Y. So that's the reason that box is important, because that this kind of mixed map actually factoring through that box. And with this extra additional condition, it is proven by Osbazhava that this map is well defined, that no matter what admissible cut you take, the image is always the same, depending on the species structure, what you are considering on the first place. So, so this is sort of a question one could ask, is that how one can think of a three-dimensional Hilbert-Floor element from the perspective of four-manifold theory, in the sense that if I fix an element in HF plus, does there exist a four-manifold W such that the image eta is in the mixed map or not? An easier version of this problem is following, that given a three-manifold Y, does there exist a four-manifold W with boundary Y such that this mixed map is non-trivial? So conjecturally, this mixed map is same as the Seiberg-Witten map in the monopole theory. So one can ask the same question, that for a given three-manifold, can you always have a four-manifold with non-trivial Seiberg-Witten solution or not? And such a thing we called floor cap. Although I don't know whether it's ever used before or not. So all that seems like a very natural question, but not much is known about this direction. And very recently, with a joint work with Etnaer and Min, we have constructed a large class of three-manifold, which has this non-trivial floor cap. That is, there exists a cap. We call it cap because it is by construction sort of coming down, where the direction of the cobordism map is towards the down. So we call it cap. So we sort of construct a very big class of three-manifold which has such cap. For example, we construct that given a three-manifold with non-trivial contact invariant, there always exists such a cap. And this cap also helpful in understand of three-manifold that are boundaries of exotic four-manifolds. That means here exotic means homeomorphic but not diffeomorphic, because now on that four-manifold you can do various operations and try to see under those operations how this floor map is changing. And maybe if you are lucky enough, you can find something where the homeomorphism type is fixed, but this image of the floor mix map is changing, and thus one can say that you can produce exotic four-manifolds.
So just a quick question. So if I have maybe you said this already, if the three-manifold is the boundary of a Stein or symplectic four-manifold or something, then is that a floor cap, or is that the wrong direction?
Yeah, so I think the intuition is correct. So if a three-manifold is in fact a boundary of Stein manifold, then it has non-trivial contact invariant, so you can always construct a cap. And I'll come to that.
But the Stein manifold is not just trivially a cap?
No, that's a filling. So in our language, that's
what it really is a cap versus a fill.
Yeah. So
and then there's all these constructions of caps for Stein manifolds, you know, involving are those, you know, various standard constructions of caps for fillings. Are they all automatically floor caps, or you have to do extra work?
So for our caps, it is almost the same way one construct those caps for Stein filling, but we at the same time we sort of track of the floor map under those cobordism as well, and that's how we construct the caps in our work with Etnaer and me.
Okay.
And as I say, so the interesting thing is that we do not know any other construction outside this particular class, and so that's the reason. So as I say, the one interesting open question one could think is that does all three-manifold bound exotic four-manifold or not? And I mean, the answer should be yes, but the problem is that how do you prove that something is exotic? So in order to prove something is exotic, you need to have something non-trivial, like either Seiberg-Witten or some kind of floor map, some non-triviality of those things, and those are not at all obvious.
So what's your definition of exotic here?
So exotic means they are homeomorphic but not diffeomorphic.
So you mean that do all three manifolds bound different non-diffeomorphic but homeomorphic cap?
Yes. Yeah.
I see.
So that means like it can given a
Once you find the cap, can you find the diffeomorphic?
You should say exotic pairs.
Exotic pairs, right? Yeah.
Yes, exotic pairs.
Pairs.
In particular, as I say, in particular, we have actually proved that if you give me a three manifold with either orientation, if y or minus y has a contact invariant, non-trivial contact invariant, then we can actually produce a four manifold W with boundary y, such that W has actually infinitely many distinct smooth structure that we can prove. So
if you have a tight contact structure?
No, we don't know. So tight contact structure does. So that's the thing we have been thinking how to. So that's the reason.
Wait. So maybe can you repeat?
He said non-trivial invariant. He said
non-trivial
contact invariant.
Okay, yeah, I didn't hear that part. Yeah. Okay.
Oh, yeah.
So non-trivial contact invariant.
Yeah. So now come back to this idea of this floor cap, and the idea is following that if I have a closed four manifold X such that this mix map on the first place is non-trivial, and if I know that my interesting three manifold is sitting in this separating way here, then I can argue under some certain condition that this mix map should factor through the HA plus of Y, and that might help us to construct this floor cap. So this part will be in that case a cap of Y. So the thing is that, do you know a class of good manifold X such that this mix map or the Seiberg-Witten equation is non-trivial? And the answer is yes. And in particular, for the Seiberg-Witten version, it was proven by Taubes, and later on for Higart-Flohr version, it was proven by Uzbat-Szabo that if X is a symplectic four manifold with B2 plus greater than 1, then Seiberg-Witten or the mix map is non-trivial. And that's the reason on the first place we actually came up with this conjecture that find that, okay, we know this class of four manifold, symplectic four manifold, where this mix map is non-trivial. So if we can embed every three manifold in this boundary separating way, then actually we can get a non-trivial cap, and in particular we can answer the question whether all three manifold bound and exotic four manifold or not, or a pair of exotic four manifold or not, or in particular an infinite number of exotic structure it has or not. So this is sort of the motivation. So anyone has any question?
So what happens for B2 plus equal 1? What can you say about F mix in that case?
Oh, so in that case, you have to take the Perturb coefficient. So that's the reason I'm not going into the B2 plus 1. So Uzbat-Szabo's Higart mix invariant under the general coefficient is only defined when well-defined when B2 plus is strictly bigger than 1. And for the B2 plus 1, in order to make it a well-defined map, you have to go through some sort of Perturb coefficient. So that is a little bit
of coefficients. Sorry, I didn't catch that.
Oh, so this is sort of, you need to perturb with some kind of F. So I think you need to perturb this thing with some sort of HF plus Y tensor C U inverse, some kind of perturbation you have to take of those maps. So yeah, so I think in our paper we also discussed a little bit about that version. So this is also, I think another reference would be Jan Zemke and Andrew Juhas. Their paper on exotic surfaces in four ball. They also did something similar to this.
Okay, so in this case, so yeah, I'm not familiar with this story, but so is there any U torsion anymore? So
sorry, which case?
So you kind of tensor so you change your coefficient to some kind of like a Novikov coefficient.
Yes, yes.
So
Some sort of Novikov ring we are taking there.
In this case, do you have U torsion? It could have U torsion.
It could have U torsion,
Okay,
yes.
I see.
Any more questions? So this is sort of the motivation, and now come back to the original problem, that embedding of 3 manifold in symplectic 4 manifolds. So I can consider a set of all 3 manifolds, and in particular, as a subset, it will be set of all 3 manifolds which embed topologically in symplectic 4 manifolds. And then I consider a set of all 3 manifolds which smoothly embedded in symplectic 4 manifolds. And then I can take one more particular embedding, which is contact embedding, where the symplectic structure behaves nicely with the contact structure of the 3 manifolds. So this last inclusion has been studied a lot in last 40 years by various experts like Gromov, Thurston, Gompf, Liska, Matic, Ekner, Honda, David Kay. Like, people have been studied this contact embedding problem a lot, and various interesting result has been proven using this sort of contact embedding. But the other two inclusion, that is in this case, these two particular inclusion hasn't been studied that much, or hasn't much attention haven't been paid on these two particular inclusion. So here is a first result about this particular inclusion, and that is following. That given a closed connected oriented 3 manifold Y, there exists a simply connected symplectic 4 manifold X such that Y can be embedded topologically locally flatly in X. Moreover, this embedding can be made a smooth embedding after a single stabilization. That is, Y can be embedded smoothly in X connected some S2 cross S2. But of course, X connected some S2 cross S2 is not symplectic anymore, because if you know a little bit about Cyber-Witten or Higart-Floor, you can easily prove that this Cyber-Witten or the mixing invariant map vanishes on X connected some S2 cross S2. So before proving this result, I want to say a little bit about the application of the proof of this particular theorem. And here I will state an interesting application. So before that, let's recall that a cobordism between two closed oriented N manifold Y0 and Y1 is actually a compact N plus 1 dimensional manifold whose boundary is Y0 and Y1. And I kind of think of that, I take minus Y0 because you oriented W, and that orientation gives some sort of orientation in Y0 and Y1. And on Y0, it induces a negative orientation, and on Y1, it induces a positive orientation. So that's the reason we consider the boundary as minus Y0 union Y1. And we call this as a R homology cobordism if the relative homology with R coefficient vanishes. So that considers the R homology cobordism. In particular, we can define this interesting homology cobordism group as all closed connected N manifold with the homology of Y is same as the homology of N sphere under this equivalence relation. And under the connected sum, this is actually an abelian group. Okay. So in low dimension topology, the study of integer homology cobordism group, that is the group generated by integer homology sphere, the cobordism group generated by integer homology sphere, and the rational homology cobordism group are of special interest. Not much is known about the generator of such groups. So it was known, so Mayer proved that these two groups are actually generated by hyperbolic 3 manifold. And here I present another new generator of such groups, which is, so theta 3z or theta 3q are actually generated by Steinfeld 3 manifolds. So here Steinfeld 3 manifold are a 3 manifold which has a contact structure, which is Steinfeld. And I'll define Steinfilling in a shortly if you are not familiar with what is Steinfillable. But one thing I would like to point out that Steinfillable three manifolds are not that common. And in particular, one thing, so I think this is first proven by Liska that there exist three manifold which is not Steinfillable, and later Etner and Honda improve and prove that there exist in fact three manifold which has no tight contact structure, and if it is Steinfillable three manifold, then the boundary so then the associate contact structure is actually a tight contact structure. So this is the another new generator that Steinfillable three manifolds are in fact generate these two homology cobordism group. So let's now talk about the proof of the topological embedding, and in particular the proof of that all three manifold generated by Steinfillable three manifold. So the idea is following, that given a three manifold, in particular given a contact three manifold, we know that the symplectic cap always exists. So symplectic cap in this sense, what I meant is that that the symplectic structure on this four manifold W prime induce, sorry, the Liouville vector field corresponding to the symplectic structure W is sort of pointing in or inwards with respect to the boundary contact structure side. And the interesting thing is that if you give me any three manifold contact three manifold Y psi, there always exists such a cap, symplectic cap. So in our construction, I am interested in constructing a simply connected three manifold. So existence of cap has been proven by many people, but we will use this particular result, which is proven recently by Etner, Min, and myself, that given any contact three manifold, there always exists a simply connected symplectic cap with B2 plus bigger than 1. So we'll use this particular cap for our construction because of the fact that it is simply connected. Now, if we can embed a three manifold Y in a symplectic filling, then we are done. So symplectic filling means now a three manifold with boundary, sorry, a four manifold with boundary, the particular three manifold I'm interested in. And now the symplectic structure actually pointing outwards. So this is the reason, so this is the difference between cap and the filling. So for the cap case, I can see that the Liouville vector field is sort of pointing inwards with respect to the boundary, whereas for the filling, the Liouville vector field pointing outward. Although the cap always exists, the fillings are very rare. And that's the reason if we can embed our three manifold in some filling. So as I said, that it is known that there exists three manifold with no filling. But if we can able to embed our three manifold in some filling, then we can cap off this filling and thus construct a symplectic four manifold. So that's one of the idea I have in mind, and I wanted to work on that idea. So Stein four manifold is a special kind of strong symplectic filling, and I'm not going to define what is Stein four manifold, but I'll give a topological characterization of the Stein four manifold, which is as follows, and which is due to Gompf and Eliasberg, that if you have a Stein four manifold, then it has a handle decomposition with 0, 1, and 2 handles, whereas the 1 handles are attached along B4, and there exists this canonical symplectic structure on one handle, which induce a unique tight contact structure on the boundary S1 cross S2. And the 2 handles are attached along Legendrian knot on S1 cross S2 with psi standard, with the smooth framing 1 less than the contact framing of those Legendrian knot. So this is sort of a topological characterization of Stein four manifold. For example, if I have this picture and this pink knot is my K on the boundary of S1 cross S2, then I can have this following two crossing of this knot K and this following two cusp of this knot K. And a Legendrian realization is following that this particular crossing is a good crossing. So if I have this crossing in my knot, I'll not change anything. If I have this cusp, I will change or convert these cusps with something like this. And similarly, so this is called left cusp, and the right cusp, I'll convert something like this. But the problem is that I cannot have a crossing like this. But notice that you can realize this crossing with help of these three as follows. So in this picture, you can see that these two crossings are actually isotopic, whereas now you can change the bad crossing with all the good crossings. And this is sort of called the front projection. The idea of the front projection, so now we can see that this particular representation has this particular front projection. And the idea of the front projection is that it helps us to count the, in a geometric way or in a topological way, to count the contact framing. So the contact framing, which is also sometimes called with some abbreviate of notation, the TB number or Thurston-Bennikin number of a knot. So from this picture, you can, the Thurston-Bennikin number of a front projection is nothing but the right minus number of left cusps. So in particular, this picture, the Thurston-Bennikin number is +2. So having this idea in mind, now we'll start the proof. So we'll try to embed a 3-manifold in a Stein manifold. So let's say Y has this representation. K1, K2, Kr are the knots with surgery description coefficient Ni, which is an integer. So every 3-manifold we know that can be represented by such a surgery representation where Ki's are the knot in S3 and Ni's are some integer. We can Legendrian realize this link L, which is union of all these knot. Okay. And we want that the Thurston-Bennikin number of that Legendrian realization has TB number bigger than the smooth coefficient Ni. If this is true, then we are done, because the result of Eliasberg and Gomes saying that, yeah, this is actually a Stein, so we can cap it. But there is no reason that this condition should be true. And that's the problem. So let's try to understand that how close we can get the Kirby picture to be, which satisfies this particular condition. So we Legendrian realize that Ki, and we sort of put, we sort of take a small Darboux ball such that all of the Ki's are kind of going from one side to the other as a parallel strand. They are kind of knotted outside of this 4-ball, but inside the 4-ball, they are just this parallel strand. So this we can always take a small Darboux ball where this picture is true. And now we want to decrease the surgery coefficient. That is, so the problem is that increasing the TB number is a very difficult job. But maybe using some smart Kirby calculus, we can hope to decrease the surgery coefficient without changing the 3-manifold. And that is what now I'm trying to do. So I'm now trying to decrease the surgery coefficient. That is, I try to decrease this part such that I can have such an inequality in my picture. Without, and one thing I need to be very careful that I'm not changing the 3-manifold in this process. So here is a very interesting concept which is known as blow up, which is following that if you have a strand with coefficient n, and if you blow up, that is, if you add this meridian a knot with framing -1, that doesn't change the boundary, but that decreases the coefficient of the knot. Okay. So in particular, I can blow up as many times as I want, so that I could have this following inequality, that now my Thurston-Bennikin number of these knots are strictly bigger than the new coefficient +2. And the reason I'm taking this +2 here has a particular meaning, and I'll come to that meaning later. But notice that I can always get this particular picture, right? That where these are all the unknot. They are kind of having in a stack, and this KIs has now the good. So now the KI knot have the good coefficient. But the problem is that this unknot has this particular Legendrian realization. And notice that the Thurston-Bannikin number of these knots are equal to now the surgery coefficient, right? Because I'm blowing up, the surgery coefficient is -1, but the Thurston-Bannikin number also become -1. That's a problem because I want my Thurston-Bannikin number to be bigger than the surgery coefficient. But while trying to fix surgery coefficient and Thurston-Bannikin relation between these knots, I create more problematic knots. That's this unknown. So what can I do? And here is sort of the idea that look at now this knot, particular this meridian. Okay. So there is this meridian. So if I now blow up this whole picture along this meridian, I get all these minus. So all these unknots now get -2 framing, which is a good sign. But there is a problem now. Since I'm blowing up, it get a twist, an extra twist here. So this is the picture I have now, that I sort of blow up and I get an extra twist. But actually we are in a good shape because this extra twist can be legendary and realizable. So notice that this is the legendary and realization of this particular picture of the purple curves, all the purple unknots with -1 twist. And in particular, K1 goes very nicely, right? Because this is a good crossing, this is also good crossing. But here is a problem again. Notice that K2 has a bad crossing. As we saw that we cannot have this crossing. And notice that now K2 has this bad crossing. And this is particularly the reason why on the first place we consider, we blow up such that TB of Ki is actually bigger than the coefficient +2. Although this is a bad crossing, we can actually stabilize Ki once because we have this particular relation. And we can have this particular picture here, such that all these knots which is passing under K, they now can pass from here. And thus you can see that we can actually legendary and realize all these curves such that the contact framing is actually one bigger than the smooth framing. So in particular, this is a Stein picture. But what happened to this knot, this red knot? So there is still this red knot gamma, and the TB number is equal to the Thurston-Bannikin number of this particular gamma. And this is a problem. So notice that, so what we have done so far, so the summary is following, that we started with a 3-manifold, and we sort of convert the description of the surgery of the 3-manifold into a 4-manifold, such that except this particular knot gamma, the complement is actually a honest Stein filling. So if somehow we can take care of the gamma, then we can hope to embed this this whole 4-manifold into a Stein 4-manifold. So how do we take care of this framing of the knot gamma? So this is our W, where except this particular knot gamma, everything is Stein. So in order to fix this knot gamma, I build a cobordism. What I do, I attach a Mazur cork. So a cork is essentially a pair of cancelling one and algebraically cancelling 1 and 2 handle. So you can see that this is the 2 handle here, and this is my dotted 1 handle, and they are sort of intersecting algebraically once together. So they are cancelling, they are algebraically cancelling. Or in other words, you can say that this manifold deformation retract onto this particular manifold W. Okay. So this is the topological idea of attaching a cork. And this core is disjoint from everything except this intersecting ones to this red node. So this doesn't fix the framing. But if I do a cork twist, so what is the meaning of cork twist now? A cork twist is essentially you interchange the two handle with the one handle. That is, you interchange the dot here with the dot here. So if I do a cork twist, now notice that the one handle, so this has become one handle and this has become two handle. But now notice that this one handle actually geometrically intersecting these two handle, this red two handle. And since they're intersecting geometrically at a single point, we can cancel them. So in order to cancel them, we first need to slide this handle on top of these two handle and then cancel. So we get this picture. So notice that everything in the complement is still the same as it is, except the red knot is now replaced by this knot. And this is actually a good knot. So this is a Legendrian realization of this particular knot. And in particular, it has now TB equal to +1, whereas the surgery coefficient is -1. So that means this is what we want, right? We wanted to have the TB number to be bigger than the surgery coefficient. So we get it. But we lost something. So when we did the cork twist on this stage, we actually lost the fact that the resultant new manifold are not immediately diffeomorphic to the one we had. But here is a good thing. This manifold was simply connected and the cork was attached on top of that. And we are doing the cork twist here. So by a result of Friedman, we can still prove that the resultant manifold, which we got here after the cork twist, is homeomorphic with the previous manifold. So in particular, we have this picture now. We had this W where one particular knot was bad or handle was bad. We attach a cork here and we applied a cork twist W prime. And we get this new Steinfillable 3 manifold now. So this is a Steinfillable because now we get everything as we wanted to have. That is, all the TB number of these knots are bigger than the smooth coefficient. So this is Stein. And thus we can cap it off and get this. So we can cap it off with a simply connected cap. Simply connected cap. And thus we get a smooth closed symplectic 4 manifold. But notice that since we are applying a cork twist, these two manifolds are now homeomorphic. So in particular, this Y was embedded here smoothly, but we cannot guarantee anymore that here the image is smooth anymore. So that's the reason we have to compromise the smooth embedding of the Y. And in particular, we get a topological embedding of Y in the symplectic 4 manifold. And also now notice that this particular stage here, where we are attaching and we are getting the manifold Y prime, this Y prime is Steinfillable, right? Because the cork twist doesn't change the boundary 3 manifold here. And in particular, this is a Steinfilling of Y prime. So in particular, we also prove that if you give me any 3 manifold, by attaching one handle and one two handle, I can always convert it into a Steinfillable 3 manifold. And that proves the fact that all these cobordism groups are actually generated by Steinfillable 3 manifold. So this is, can I have 5 more minutes or? Okay. So this is the part. So anyone has any question before I jump to the smooth embedding part?
Well, just quickly, I never thought about this before, but the homeomorphisms constructed by Friedman, it's not obvious that a homeomorphism composed with a smooth embedding would give a topologically locally flat embedding.
Yes,
A
but
locally flat thing, is that sort of an obvious consequence to the, those who know at least about?
yes. But in this particular picture, actually, this is locally flat because if I go back to the Kirby picture, the only problem is this two handle going past to the one handle, and this has a locally flat representation. So that's the reason you can, because the three manifold is sort of this thing, right? This is the three manifold, which is,
Well, but I don't know how crazy that. I mean, you're
Oh, yeah.
composing a smooth embedding with a homeomorphism, and I have no idea how crazy that homeomorphism is. For all I know, it makes everything. And I mean, I know it doesn't really do this, but I could imagine there are homeomorphisms that wrinkle everything.
yes, and that's the reason. Yeah.
You're saying somehow that's like that doesn't happen at this place.
Yes, somehow that doesn't happen. In particular, that's the second part, that in particular, by a single stabilization, you can fix that problem.
Okay, we'll keep going. I
Yeah. So okay. So I'll not go to the single stabilization proof. This is more Kirby calculus, but it is, if you are patient enough with Kirby calculus, you can actually prove that with a single stabilization, you can actually fix this crazy thing. If anyone interested after the talk, I am happy to present that part. So here is now let's quickly focus on the smooth embedding part. So quickly recall that a rational homology sphere we called L space if the reduced homology Higger-Floor homology is 0. That means the Higger-Floor homology is just a tower. So you can keep the example of S3 in mind. Okay. And here is an interesting result, which sort of kind of giving how smooth embedding now behaves with the topology of the symplectic 4 manifold. So this result is saying that if Y is an L space which embeds in a symplectic 4 manifold X, then Y has to be separating. And in particular, if Y separates X as X1 union X2, then one of the Xi has to be a negative definite 4 manifold. So one can see now that how to smooth embedding actually restrict the topology of the symplectic 4 manifold. That is, you cannot embed in a non-separating way, and moreover, both the pieces cannot have B2 plus bigger than 1. Okay, so using this idea, one can prove this following interesting result, that there exists 3 manifold Y which cannot smoothly be embedded in any symplectic filling of a 3 manifold. And I'm using a star because you need a small condition here when we are talking about smooth embedding of a 3 manifold with orientation. There is something we need to keep in mind, but this is a very small restriction. And it's saying that in particular, there exists 3 manifold which not only has no fillings, but which actually cannot be embedded inside any fillings. So as I said that existence of manifold with no filling were known before. And this is somehow stronger than that, because this saying that not only this manifold has no filling, but actually you cannot even embed them smoothly inside any filling of a manifold. And one last thing I would like to state is following, that this smooth versus topological embedding in particular help us to even understand exotic structure on a 4 manifold. For example, we can prove that there exists a compact 4 manifold X1 and X2 with B2 equal to 1. That is the second cohomology is very simple, which are homeomorphic but not diffeomorphic. It was first proven by Akbulut using results of Donaldson's and various other flow theoretic versions. And I gave an alternating proof of that using the idea of smooth versus topological embedding of 3 manifold in 4 manifolds. And I think I'm now running out of time. So this is the end, and I'm happy to answer any of the question. And if anyone is interested in knowing any of the proof, I'm happy to sketch.
Let's thank Anubhav right now. And are there any questions?
Hey, so you know that I mean, we know there are 3 manifolds that support no tight contact structure. So what happens for those manifolds? You're just you're adding 1 and 2 handle, and I mean 3 manifolds. You're adding like sigma 235 or something. You're adding a 1 handle and a 2 handle. And how are you changing? How does that change the manifold?
So it depends on, so as I said, that if you give me a 3 manifold, you sort of, so then I need to first start with a surgery description of that 3 manifold.
Right.
And then I need to track that bad knot. So as I said, this is sort of a combinatorial idea. But if you now give me a surgery description of that 3 manifold, I can easily construct.
Okay, so you just hang this.
Yes. So for example, so let me go. So I had prepared a few more slides, but let me talk about this particular example. For example, Poincare homology sphere with reverse orientation has no tight structure.
Right.
So here is a description of that. I think it's a +1 surgery on right hand trefoil, right?
Yeah.
So this is +1. So this is not tight. But now what I can do? So now notice this 3 manifold. So notice these 3 manifold. So this is let's say P prime, and by construction there is this P prime. This is the homology cobordism, and P prime is no Steinfillable, because if you slide this handle over this, that will increase the TB number by +2, and you can have a good representation of P prime by handle calculus.
And so now you have the Stein filling, and you know that in manifold with a Stein filling.
Yeah, but as I say that also, so this is the result. So as I say that so for example, so as I say, mostly I thought about Poincare homology sphere with negative orientation. So in particular, one can prove that Poincare homology sphere with negative orientation cannot smoothly embedded in any weak filling omega prime of.
Yeah, I think that was known, right? Because it was known that it doesn't embed in a symplectic manifold. Like, is it pin to shell stern or something?
Yeah,
Like,
but the thing what was not known is that it could have still be embedded in a non-separating way, right? It was known that the filling doesn't exist, and that is because kind of arguing that it is then separating in a symplectic 4 manifold.
Right.
But the new case is essentially it could still be a sort of a non-separating embedding, and this is the new.
How do you prevent it from being a non-separating embedding? I didn't.
Oh, so this is a little bit long proof, but I can sketch the proof. So let me sketch. So here is the sketch of the proof. Okay. So okay, so I'll prove that if y is an L, so in particular I'll prove this result, that if y is an L space, then it cannot be a non-separating. Okay, and and the second part was known before. So this
Right.
part was originally proven by Osbert Szabo and also by Liska Matic for monopole simplex cyber-Witten theory. Uh, so the new part is this part, that it cannot be a non-separating. So this is in particular the new part, and here is the pictorial proof. So I'm not saying everything in details, but I'm drawing the picture. So let's assume that it is non-separating. So this is my x, and y is sort of non-separating. What I do is that I cut open x along y, and then I glue two copies together. So I have this. Also notice that since it's a rational homology sphere, from Meyer-Vettori homology calculation, it's easy to prove that B2 plus of both the pieces are strictly bigger than equal to 1, because I already have a symplectic
I
structure.
guess I would separate those things and draw it as a torus, right?
Oh
Right.
yeah, you can do. Okay, yeah. I mean, that is also doable.
Because that, I mean, those two things go separate completely.
Yes. Yeah, that's true. Now notice that this is in fact an honest twofold cover of the original 4 manifold X. Right. So this is actually an honest twofold cover. And we know in particular that X is symplectic. So we can actually now pull back the symplectic form. So in particular, that saying that X tilde is symplectic. And in particular now, from this picture, I can see that this red separating is actually Y connected.
Can you please draw it so that they're separated and they don't touch? Because I don't understand this picture.
Okay.
I would really like to understand. So.
Okay. Sorry.
Thank you.
Let me.
Just draw it like an annulus rather than.
Right.
Yeah. Let me do that. So let's say this. This is X.
Right.
And I kind of cut open X.
Right, because if it is separating, therefore there is a curve that intersects it once, right? So we can do double.
So now this is the double cover of X. Okay.
Yeah.
So in particular, this is symplectic.
Right.
Okay. Now you can sort of tube these two things, and also notice that B2 plus is bigger than equal to 1 in both the pieces, right? Because I have a symplectic form omega such that omega wedge omega is bigger than 0, positive. And since this is a rational homology sphere, so this has since this is a rational homology sphere, so that could not destroy the homology or the cohomology, if the free homology or cohomology. So the B2 plus is still bigger than equal to 1. And in particular, now I sort of can tunnel these two boundary, which sort of away from the generator of such homology. And now notice that this is sort of this new thing. So let me draw in this way. So this is now separating. And this is nothing but Y connected sum minus Y. So this is now sort of separating, because if I use a color, so this is sort of.
Right, it's non-separating because.
So this is this. So this is so now we can see that Y connected sum minus Y is separating of X tilde, right? So another picture one can think of now, this Y connected sum minus Y, and this is X tilde. And also notice that now B2 plus by construction is strictly bigger than 1 in both the pieces, right? So by so that means what? And this is now an L space, right? But an L space cannot be an admissible cut. So So that means then the Cyber-Witten or the mix map vanishes. But this is symplectic. So by the result of taus and Kurzbach-Szabo, the mix map or the Cyber-Witten map cannot be vanished. So this is a contradiction. So this is a contradiction of our basic assumption of this picture. That means this is the wrong picture. So that means this manifold cannot be.
Yeah. All right, that's cool.
Any other questions? Let's thank Anubhav one more time, and then if people want to stick around, we can chat. So great. I'm gonna pause recording. Stop.
So